Imagine an aircraft so advanced it could fly into enemy territory completely undetected. A plane that doesn't just drop bombs, but disappears into the night sky like a ghost. This is the B-2 Spirit, America's legendary stealth bomber. But how is this mysterious flying wing actually built? Today, we'll dive deep into its secret origins, groundbreaking engineering, and the unbelievable story of how the U.S. created the most expensive warplane in history. The B-2 Spirit stealth bomber is widely regarded as one of the most extraordinary feats of modern military aviation and engineering. Its origins trace back to the Cold War, a period defined by intense geopolitical tension and technological competition between the United States and the Soviet Union. The development of the B-2 was driven by an urgent need for a new kind of strategic bomber that could evade increasingly sophisticated radar and missile defenses. By the 1970s, the emergence of new Soviet radar systems and surface-to-air missile technologies threatened to render conventional bombers vulnerable. To maintain strategic deterrence and offensive capability, the U.S. Department of Defense sought a revolutionary approach, an aircraft that could operate undetected deep inside hostile territory. This vision led to the development of stealth technology and ultimately the conceptualization of the B-2 Spirit. The project was entrusted to Northrop Grumman, a company with a history of pioneering advanced aircraft designs. Development was conducted under a cloak of extreme secrecy, with contractors, suppliers, and technicians often unaware of the full scope or purpose of the components they produced. The bomber was unveiled publicly only in 1988 after more than a decade of classified research and development. This marked a pivotal moment in aviation history, introducing an aircraft whose very shape and materials were meticulously designed to evade radar detection. The primary mission of the B-2 Spirit has always been strategic deterrence and long-range precision strike. Its stealth design allows it to penetrate heavily defended airspace and deliver nuclear or conventional weapons without prior detection. This capability provides the United States with a critical advantage: the ability to project overwhelming power with reduced risk to the aircraft and crew. During the Cold War, the B-2's nuclear strike capability was paramount, ensuring a credible second strike option to deter nuclear aggression. Post-Cold War, its role expanded to include versatile conventional bombing missions in conflicts such as Kosovo, Iraq, and Afghanistan, showcasing its ability to strike high-value targets with extraordinary precision. Unlike earlier bombers, which relied heavily on electronic countermeasures and speed for survivability, the B-2 uses stealth technology as its primary defense. The aircraft's ability to operate discreetly forces adversaries to adapt tactics or invest heavily in counter-stealth technologies, impacting global strategic balances. The B-2 Spirit's design philosophy combined aerodynamic excellence with advanced stealth technology, departing radically from traditional bomber profiles. The B-2 employs a flying wing configuration that removes vertical stabilizers, tail fins, and other protruding features that typically reflect radar waves. This flying wing shape results in a smooth, continuous surface that greatly reduces the radar cross-section, the measure of how detectable an object is by radar. Aerodynamically, the design is optimized to maximize lift and minimize drag, which increases fuel efficiency and range. This allows the B-2 to operate globally, with an unrefueled range exceeding 6,000 nautical miles and the ability for mid-air refueling for virtually unlimited reach. Internally, weapon bays house a wide array of ordnance to maintain stealth. By carrying weapons inside, the bomber avoids the radar reflections caused by externally mounted stores. The careful shaping of every panel and edge prevents radar waves from bouncing back to the source, and meticulous surface finishing eliminates tiny gaps and irregularities that could increase detectability. The balance between stealth and aerodynamic performance required unprecedented precision in computational fluid dynamics, CFD, simulations, and wind tunnel testing. Designers had to ensure that stealth features did not compromise flight stability or maneuverability, resulting in one of the most carefully engineered airframes ever produced. Achieving stealth and performance depended heavily on material science. The B-2 structure incorporates high-grade titanium alloys and advanced composites selected specifically for their lightweight strength and radar-absorbing characteristics. Titanium provides exceptional strength-to-weight ratios, allowing critical structural components to withstand high stresses during flight. However, the material is difficult to machine and requires specialized fabrication techniques to avoid introducing flaws. Composite materials, especially carbon fiber reinforced polymers, CFARP, play an essential role. These composites not only reduce weight, but can be engineered at the fiber and resin level to absorb or scatter radar waves, significantly reducing radar reflection. These radar-absorbent composite layers are integrated into the aircraft skin and internal structures. Each sheet of titanium or composite goes through rigorous inspection. Laser scanning and ultrasonic testing detect microscopic cracks or imperfections that could undermine the bomber's stealth or structural integrity. These inspections are performed at every stage, ensuring only flawless materials proceed through production. Supply chains for these materials are carefully managed to maintain secrecy and consistency. Often, suppliers are unaware of the final application of the parts they produce, and every shipment is tracked under strict chain of custody protocols to prevent leaks. The manufacturing begins with the preparation of raw materials. Titanium sheets arrive at the factory and undergo thorough inspection through ultrasound and laser scanning to detect any internal defects invisible to the naked eye. Even the smallest imperfection could compromise a component's strength or stealth function. Composite fibers, often carbon-based, are similarly inspected. These fibers are laid up in multiple layers to create panels tailored in thickness and radar absorption, then cured at controlled temperatures and pressures to develop strength and desired electromagnetic properties. Once validated, the raw sheets and composite panels are cut using high-precision computer numerically controlled CNC machining centers. These tools programmatically slice the materials into complex shapes compatible with the bomber's unique geometry. This process minimizes waste and ensures tight dimensional accuracy critical for later assembly stages. The hardened titanium pieces are kept in secure, monitored environments between cutting and fabrication steps to maintain quality and secrecy. Component fabrication transforms raw materials into the myriad parts that compose the B-2's airframe. Titanium sections are machined using precision tooling that incorporates temperature controls and vibration dampening to prevent microfractures. Composite parts are built by layering carbon fiber cloth impregnated with specialized resins in molds shaped to exact specifications. These parts are then cured in autoclaves, giant pressurized ovens, to achieve maximum strength and uniformity. These environmentally controlled cycles prevent warping or uneven curing, which would degrade stealth capabilities. Many fabrication steps employ robotic machining for repetitive or delicate operations, ensuring consistency beyond human capability. However, skilled technicians perform final finishing and inspection, blending automated precision with expert judgment. Holes for fasteners and joints are drilled with microscopic accuracy so that parts fit seamlessly without gaps or misalignments that could reflect radar or degrade structural endurance. Throughout fabrication, a comprehensive tracking system logs each part, from raw material through subcomponent to final shipment to assembly, maintaining stringent chain of custody safeguards. Assembly of the B-2 Spirit is a marvel of mechanical precision and coordination. The process begins with the central fuselage section, extending gradually to the expansive wing structures on either side. Highly automated robotic arms position titanium and composite panels to align within fractions of a millimeter. These panels are then welded, riveted, and bonded using cutting-edge adhesives specially formulated to maintain strength while preserving stealth characteristics. Throughout assembly, laser tracking systems measure every joint and surface, comparing the airframe's shape to digital blueprints. If alignments fall even slightly outside tolerance, the components are adjusted or remanufactured to uphold drastic stealth requirements. Integration of internal systems follows structural assembly. Wiring harnesses run miles along shielded conduits, connecting avionics, radar-absorbent sensors, navigation computers, and electronic warfare devices. The integration phase also includes installation of fuel systems, hydraulic lines, and life support systems for the crew. Every assembly step passes through rigorous quality control, with engineers inspecting welds, adhesive bonds, and fasteners under high-powered microscopes. The result is an airframe that appears almost seamless, featuring smooth, unbroken surfaces vital to avoid radar detection. The hallmark of the B-2 Spirit is its stealth capability. This is achieved through a combination of shape, materials, coatings, and internal component arrangement designed to minimize radar cross-section, RCS. The smooth flying wing shape directs incoming radar waves away from their source. Sharp edges, corners, and vertical stabilizers common in conventional aircraft are eliminated entirely to remove radar reflective surfaces. Radar absorbent materials are woven into the aircraft skin and structure to soak up radar energy rather than reflect it. These materials contain magnetic and conductive elements that convert radar waves into heat or dissipate them harmlessly. A special radar absorbent paint is applied in multiple thin layers by hand under strictly controlled conditions. Environmental filters maintain purity to prevent dust or fibers from embedding in the coating, which would increase radar signature. The paint also protects the airframe from corrosion and wear in harsh atmospheres. Internal weapon bays keep ordnance hidden from radar and infrared detection, differentiating the B-2 from bombers that carry weapons externally. The B-2 Spirit is outfitted with state-of-the-art avionics that support its stealth mission and enable complex navigation and targeting in contested airspace. Miles of wiring and advanced circuits run through shielded spaces to connect flight control computers, radar-absorbing sensors, threat detection systems, and communication arrays. These systems allow pilots to plan and adapt precise missions, avoid detection, and counter electronic threats. To ensure resilience, redundant control systems provide backups in case of hardware failure or electronic attack. Highly secure software is constantly updated to respond to emerging threats and include the latest navigation and targeting protocols. The complexity of these electronics requires constant testing and validation, conducted under strict security to protect sensitive technology. Before the B-2 Spirit can enter service, it undergoes exhaustive testing and quality assurance. Each component passes bench tests to validate strength and stealth properties. Once fully assembled, the bomber is subjected to ground tests for structural integrity, avionics functionality, and radar cross-section measurement using specialized radar facilities. These tests confirm that the stealth profile meets or exceeds design specifications. Flight testing includes taxi drills, takeoffs, and extensive in-flight maneuvers under simulated combat conditions. Pilots monitor performance, while engineers collect data on aerodynamics, engine response, avionics, and stealth effectiveness. Only after clearing every test stage is the aircraft approved for deployment. Since its induction, the B-2 Spirit has redefined strategic bombing. It has been successfully deployed in numerous conflicts worldwide, demonstrating its ability to strike with precision while evading enemy detection. Its participation in conflicts in Kosovo, Afghanistan, Iraq, and other theaters has proven the bomber's value beyond nuclear deterrence. The B-2 can deliver a wide range of munitions with minimal collateral damage. The bomber's very existence has influenced global military strategy, pushing rival nations to research counter-stealth technologies, thereby advancing the arms race further. Maintaining the B-2 is a continuous and meticulous process. The advanced materials and coatings require specialized care to preserve stealth characteristics. Electronics and software are upgraded regularly to counter new threats and incorporate improved systems. The modular nature of onboard systems allows for relatively quick integration of new technologies without complete overhaul. Highly classified maintenance protocols protect the bomber's secrets while ensuring operational readiness for many decades. The B-2 Spirit stealth bomber represents the pinnacle of human engineering, technological innovation, and strategic foresight. It transformed aerial warfare by demonstrating that invisibility on radar is achievable through shape, materials, and advanced manufacturing. Beyond its weapons capabilities, the B-2 Spirit was more than just a bomber. It was a message, a message to America's enemies that no matter how advanced your defenses, you could never see the ghost that haunted your skies.